I'm going to present you the chemistry of iron and the Fenton reaction. This is really a very wide group of treatments. The most important, maybe the most widely employed, is Photo Fenton, but also some other related treatments also involve iron. Okay, so some of you are using continuously Photo Fenton in your PhD, in your work. Other one maybe are quite far from this. So I try to explain you which is the. ¿Esto cómo se pasa? Well, iron can be found about the most abundant elements of Earth, and the chemistry of iron is very complex. It's very complex because of two different features. One is the ability of iron to form complex with a lot of ligands. So this means that a lot of species of iron can be found in the environment. Okay, and the other second characteristic is the different oxidation states that can reach iron. For instance, you can have zero-valent iron. You can have iron in the oxidation state of 2, the oxidation state of 3, but also we can find some other exotic species of iron, iron 4, iron 5, iron 6, and even some species, for example, magnetite, mixes iron 2 and iron 3. So we have a wide amount of compounds having iron in the structure. So these species show very different physical and chemical properties, and they can be employed. Okay, they can be used in pollutant removal through different processes. For example, coagulation, flocculation. Iron is known to be a very good flocculant. Okay. Also in catalysis, not only photocatalysis, but also in catalysis in different ways. Some catalysts contain iron, and also some, and this is something that is a little bit of a fashion now, you can put magnetic cores to the particles so that they can be removed after the reaction. So this is another possibility of using iron. Then you can use iron in photocatalysis, and photocatalysts contain iron. We also can employ iron in reductive processes. For instance, zero-valent iron, elementally iron, has the property to reduce some functional groups. And finally, you can use Fenton and photofenton and related reactions. Well, I don't know what is happening. Just going to give you some example of other treatments based on iron is the use of zero-valent iron. Elemental iron can act as mild-reducing agent. So if we are talking now about oxidative processes, why to deal with reductive processes? Well, because there are some functional groups that are strongly deactivating the oxidation of the molecules. For instance, the nitro groups, the sulfonate groups, are able to deactivate the oxidation of the benzene moieties. So we can, as a first step, to reduce these moieties and then to perform an oxidation. This is one possibility we have. We can employ very easily available species of iron, of elementary iron, for example, steel wool. We can also employ nanoparticles, iron nanoparticles. So we have plenty of substances that can be employed for this purpose. You can see here, then, for instance, you can see here how we can reduce the nitro group into the amino group, and the formation of this amino group, although it is toxic, is more easily oxidizable than the initial nitro group. However, we are now going to focus on the Fenton processes. The Fenton processes is based in the ability of iron 2 to decompose hydrogen peroxide into highly oxidizing species. Although the mechanism is very controversial, and a lot of people think of the involvement of highly oxidized iron species and the involvement of a wide range of radicals, it is quite established that It is highly established that the hydroxyl radical plays an important role in the process. Here, this reaction occurs. Okay. However, once you have all the iron oxidized into iron 3, we have no more iron 2. So this would not be a catalytic process. In order to make iron catalytic, you have to close the process. So you need another reaction to reduce the formed iron 3 into iron 2. So how can we do it? This can be this can be done in the dark. The process is again complex, but we can think about this reaction. However, the radical formed here is not very active, is not a strong oxidizing agent, and the reaction is quite slow. So in order to make this process efficient, you have to heat. So we have thermal Fenton or dark Fenton. Okay. The other possibility is to use the Photo Fenton processes. We can accelerate the photo reduction of the reduction of iron 3 into iron 2 by the photo reduction of this species you can find here. This species, upon irradiation with light with wavelengths below 500 nanometers, can be reduced, and then you have iron 2 again to put into the cycle, and then you have more hydroxyl radicals that can be employed. So please take into account that in case we have Photo Fenton, the key species is this one. In order to have a very fast or quite fast reducing space, you should have this species in the medium. Okay. Afterwards, I will tell you that we can have some substitute species that can play some role in the process. Okay. So here you can see the cycle. You can see the cycle as a general. You have here the hydrogen peroxide, which is decomposed into 2 hydroxyl radicals, and you can see that iron moves from the oxidation state of 3 to 3, and then back to 2. Okay, this is what is happening. Here you can see some reactions. You can see what is the difference between one Fenton and Photo Fenton. This reaction has been obtained with enrofloxacin, which is an antibiotic. You can see that upon photolysis there is very, very low decomposition of this compound. The Fenton reaction is able to oxidize this compound, and the Photo Fenton is able to accelerate the process. Please take into account that it is something that usually happens. At the beginning, there is a fast reaction, because even Fenton and Photo Fenton is able to drive the process, because you have plenty of iron 2. As far as you have lower amount of iron 2, you need irradiation to close the cycle. Okay? This is something you have here. Something that we have to take care, iron. Iron is a catalyst. A catalyst, you can add very, very, very low concentration of catalyst to drive the process. However, if the concentration of iron is very low, so the process could be inefficient. So sometimes ago, 10 years ago or something like this, people used to add concentration of iron about 50 to 100 milligrams per liter. Now we are moving to lower concentration of iron, and in most cases, concentration are commonly below 10 milligrams per liter. For instance, you can see the reaction has been reached with 5 milligrams per liter. It has been irradiated with simulated sunlight. You have concentration of 5 different pollutants. They are pharmaceuticals. The concentration of each is 5 milligrams per liter, so we are able to treat 3 milligrams per liter of compounds in just 30 minutes. So you can see the low concentration of iron are able to drive quite an efficient Photo Fenton process. What can we do with hydrogen peroxide? Is hydrogen peroxide the catalyst? Is also a catalyst, or we should add a stoichiometric amount of this oxidation agent? We need to add a stoichiometric amount at least of this oxidation agent, because it is destroyed in the reaction. Okay? It is the actual oxidation agent in the process. So we add a lot of hydrogen peroxide, so we are sure we have enough hydrogen peroxide. Is it wise, or this is a problem? This is a problem, okay? We have to control quite well which is the amount of hydrogen peroxide, because if we add very low amounts of hydrogen peroxide, we run out of a reaction. So the reaction at the beginning proceeds and then stops. Okay? This is something that happens when we have too low concentrations. So in case we add very high concentrations, the problem is the hydrogen peroxide itself can react with the hydroxyl radicals. So it's competing with the substrate, it's competing for the oxidizing species for the substrate. So we can find that beyond this point, the reaction is no longer enhanced by the presence of higher amounts of hydrogen peroxide, but the efficiency of the processes can even decrease. Okay? So What can we do? We have to calculate what is the best relationship between iron pollutant and hydrogen peroxide, and in any case, we can also dosage the amount of hydrogen peroxide throughout the process in order not to have too high or too low concentration, okay? This is something that you could do once you scale the process. Of course, when you are working with 100 milliliter reaction, this is not possible, okay? And then the other parameter which is important in Fenton and Photo Fenton is the pH. The pH has to be controlled because, as I told you before, in the case of Photo Fenton, the key role is due to this species. And where is this species occurring? Just around 3. So if you move to higher, if you go before this is no longer, this is not usual, you go to acidic, highly acidic process, then you have not this species, so the reaction is lower. And if you go to more, and this is more convenient, if you go to neutral area, then you don't have this, but you have other species that are not efficient to drive photofenton. The problem is not actually precipitation and formation of this species. If this species is active, you will no longer have an homogeneous photofenton, you will have a heterogeneous photofenton. The problem is that these species are not able to drive a photofenton process. They are able to drive other processes, but not the photofenton processes. So everything is ruled by the coordination sphere of iron, and this is difficult to predict what is happening. Okay, so you can see how the reaction changes dramatically when you change the pH. Here you can see the reaction I showed you before, the removal of enrofloxacin at pH 2.8, and then the removal at pH 5. You can see that the reaction is stopped. Okay, we have some reaction, but however, this is much lower as it used to be at 2.8. However, the process is even anormally efficient at pH 5 in this case. Okay. The effect of the water matrix, this is also important. Normally we do not only have water, distilled water there, but we also have another species in the sample, and in some cases this species, the sample is very complex. So we have to take care of it. For instance, some organic compounds can compete with the substrate, with the hydroxyl radical. If we have a lot of organics, then the amount of hydrogen peroxide of the reactive species is exactly the same and has to compete with different species. So it is more difficult, that it is more unlikely that this reactive species finds our pollutant. So this is one possibility. However, we have some species that are able to complex iron. In case this species complex iron, they can form a photoactive species, so can replace the key species I told you before, and to give a photofenton-like processes that it's able to extend the application of photofenton into milder values. So this is something that can be taken into account, as I told you afterwards. What happens with inorganic ions? The inorganic ions can also have a strong influence in the process, for instance, chloride, for instance, also carbonates, because they can react with the reactive species, and we have two possibilities. There are different possibilities. One possibility is that they change the coordination sphere of iron, okay, and then we do not form longer the hydroxyl radicals, but we form, for instance, chlorinated radicals. And the other possibility that it is described is that the hydroxyl radicals that is formed is finding more easily the chloride and then to form a chlorinated radical instead of reacting with the compounds. However, in both cases, we do not have the hydroxyl radical, but we have other species. This is good or bad? It is generally not good because the hydroxyl radical is very efficient, but as Marco told before, these species in some cases live longer in the time, so they are more likely to find the substrates. So, although it is not common, in some cases, for instance, carbonates can have a positive role in the process. It's unlikely, but in some cases it can occur. Okay? Here, for instance, you can see the removal of 4 different pesticides in the presence and in the absence of chloride, and you can see that in all cases there is a decrease of the pseudo first order rate constant to 1/2 of the initial value. So you can see that here the chloride has an important inhibitory effect. On the contrary, here you can see the results obtained when treating a mixture of phenolic compounds. You can see here you can see the plot. This is a three-dimensional plot when you have the time required to decrease the initial concentration of the phenols to 75% of the in a 27. In a 25%. It means that only remains in the solution 25% of the initial value. Okay, you can see that the shorter the time, the more efficient is the process. Okay, and you can see here that we would expect that the best reaction would occur at 10.8. 10.8, sorry. And you can see that it is shifted to values 3 point something, even close to 4. This is most probably due to the complexation of iron with the phenolic compound that allows the extension of the Photo Fenton processes toward milder values. This is something you have to take into account, that although it is described that the best pH for Photo Fenton is commonly 2.8, this is not necessarily so. Okay, in some cases it can be shifted some parts, okay, to 3 point something, and it could be important in some cases, okay? Photo Fenton can be driven, Fenton and Photo Fenton can be driven just with iron or can be driven with other compounds. Iron is not special, although Photo Fenton with iron is very efficient. Although other transition metals are able to drive Photo Fenton or Fenton-like processes. For instance, copper, for instance, manganese, for instance, cobalt, for instance, nickel, okay, even chromium. However, what is the major, as a matter of fact, now there is quite a lot of people, it's a kind of fashion, trying to look for Photo Fenton-like processes with copper nowadays. Okay, why? Because copper is soluble and copper is active even at milder pH. So, however, what is the major disadvantage of using copper, using nickel, using chromium? The toxicity of these metals versus iron. Okay, so we cannot employ anywhere this kind of metals. However, this is something we can take into account because maybe we have these metals in a given solution and we can benefit from it and then to remove the metals. However, this cannot be employed everywhere, but it can be taken into account for some niche applications. For instance, we did something like this quite a lot of time ago here in our research group. It was maybe 12 years ago. Here is the removal of surfactants with Photo Fenton processes with iron and with chromium. You can see that iron is more efficient than chromium, but however, chromium is able to drive some Photo Fenton. And we are working at the optimal conditions for iron, okay? So maybe if we work in other conditions, we can even change the efficiency. And this is also funny. We treated cyanides via a Photo Fenton-like process. Okay, Photo Fenton has to be employed at highly acidic pHs, and this is completely incompatible with cyanides. Cyanides cannot occur at acidic pH. Okay. However, where can we find other metals and cyanides in metal finishing effluents? In metal finishing effluents, we can have the metals and the cyanide, which is used to complex these metals and to keep them in the solution. So we decided to treat them. We put some hydrogen peroxide, we put it in the solar plant, and we see that was a very intense change of color. You can see here the very intense change of color, a very strong oxidation of the cyanides, and then precipitation of copper. The water has important amounts of copper, and we observe the detoxification of the effluent. What happens if we have very high concentration of pollutants? In case we have very high concentration of pollutants, well, we can mineralize the solution. You can read in the books that Photo Fenton is able to mineralize pollutants and so. However, this is not possible because it would require very long irradiation times in case we are able to oxidize completely all of them, okay? So this is not a realistic goal, but we have to find another goal. In case we have to work with highly loaded water, we have, of course, to work in the close to the optimum, and then we have to find what is the end of the processes. And the end of the processes would depend on the posterior use you have to do for the water, okay? In case you want to discharge this water into wastewater treatment plant, you have to increase the biodegradability. In case you want to use it for washing, the water has to be the good ability for washing. In this case, for instance, we use textile waters, we treat them with Photo Fenton, and then we employ them for another dyeing process. And you can see here that the results were very similar. So this is another possibility to employ them for this type of purposes. Here, you can see what is the removal of a mixture of pesticides. In this case, they are at 50 milligrams per liter each. That means quite a high concentration of pollutants. You can see that they are completely removed after approximately 25-40 minutes, but the amount of organics in the medium is still very high. However, we decided to study detoxification according to different methods, and you can see that according to the methods based in inactivated sludge, detoxification occurred approximately after 40 minutes of treatment. So maybe this could be the best point to cut the treatment and then to use a biological treatment. Okay, this could be a possibility. What happens if we treat with pollutants at very low concentration, nanograms, micrograms liter? Okay, in this case, you can see, it is not wise to go to pH 2.8, but it is better to try to work to more milder conditions. However, this is not so easy. You can see here the removal of 5 compounds, and here is the photolysis. Here is Photo Fenton at pH 10, and you can see that those are hours. And here you can see the reaction at pH 7 in the presence of humic substances, because we took water from a water. It contains a high amount of humic substances. These substances are able to complex iron and to drive Photo Fenton a little bit efficient. However, you can see that still they are hours. Okay? Yes. So, in case we want to move to milder conditions, we have to work in such conditions that we are able to prevent the formation of these species that inactivate Photo Fenton. Okay, so we have to prevent the formation of these oxides or hydroxides. How can we do it? We can employ different things. To use low iron concentrations, for instance, very few milligrams per liter, very few, even less than 1 milligram per liter. It is the Photo Fenton is is not efficient, but however, if the concentration are in the range of micrograms per liters, maybe they can work. Taking advantage of the sample matrix, as I told you before, maybe there are some complexing agents in the matrix. Use of complexing agents. In situ generation of iron salts, as I told you before, zero-valent iron, for instance, suffers corrosion, and the corrosion releases iron in the solution that can replace continuously the iron that is being deactivated. Heterogenization. In some cases, iron can be heterogeneous forms of iron. However, in this case, you have to be careful because in most cases, it's not a heterogeneous iron, but it's the amount of iron that is released in the sample. This is not a problem for the technical point of view, but you have to be careful about it. And we can use other metals. Well, this is, I told you before, complexation. We can use as complexing agents also small molecules. You can also employ macromolecules, for instance, humic substances, fulvic acids, chitosan, substances of this. Here, something about humic substances that are found in natural waters. And here you can see some results, how, this is the end, okay, just two slides. This is the end. These results have been employed using humic-like substances. And here you can see the time required, again, in this case, to decrease the initial concentration of pollutant to 50% of the initial amount. You can see here that the lines, although there is a decrease in the efficiency of the process, you can see it, okay? However, the decrease is not very remarkable until pH 5 in the presence of these humic substances. So we are able to extend photofenton with some loss of efficiency, of course, but with an acceptable loss of efficiency until pH close to 5, okay? Again, in this case, you have to take care into the operational parameters. Okay, we add humic substances. We add a lot of humic substances. What is happening if we add a lot of humic substances? We have negative effects. With negative effects, we have they can play an scavenging role because they can react with the hydrogen radical. They can also play an inner filter effect because they have some color. So an excess of humic substances would represent a decrease in the reaction rate. Okay, we also have some other. There is a mixture of effects. So it's very difficult to predict if these humic substances are positive or negative for the process. And this is the end of Knowledge Generalitat Valenciana for supporting this school and the European Union through a quality and all projects. And that's all.